So there are a variety of different ways to find a probability. One of them is using analytical formulas, like the binomial formula, which we are going to talk about today. Or by the time you're watching this video, we may have already talked about. These are great when they exist because they give us exact values, but some things don't have a formula, or the formula may be really complicated. We can do empirical estimations from accumulated existing data or gathering the data ourselves. But if the data doesn't exist and it's not easily collectible, then this is not useful. Physical simulations can be time consuming, maybe impossible. Computer and calculator simulations using random digits can be useful. As the number of trials increases, the estimate should get better. And with a computer, we can simulate many, many trials in a short amount of time. We have to be able to assign numbers to outcomes. The relative frequency theory of probability is the underpinning of simulations. And with computers, like I said, we can simulate something several thousand times in under a second. So, full simulation should state the problem, question, experiment to be studied. State any assumptions like independence. Usually we're assuming independence, but we need to, if that assumption is not warranted, we need to mention that. Are we allowing repetitions? Again, usually if we're assuming independence, then that would be repetitions allowed. But it may be true that repetitions would not be allowed under the circumstances that we're looking at. Assign digits to represent outcomes. Determine how many times you're going to do this. And then simulate many repetitions and state your conclusion. So assume a basketball player has a 60% free throw rate. I am so tired of basketball examples. Why do we have so many basketball examples? Use 40 trials to estimate the probability that she makes 5 out of 5 free throws. So the probability that she makes 5 out of 5 free throws, we can do that with with mathematically. But to do it with a simulation, right, we're going to assume that her free throws are independent and unaffected by things like cheering crowd, fatigue, etc. So each of these independent has a probability of success of 0.6. We're going to take a random digit table. We're going to pick a random place to start. And so a 60% chance of making the free throw, we'll say those are the digits 0 to 5. And then 0 to 9 are the chances of not making a free throw. So we're going to read 5 numbers and count how many free throws she makes out of 5. And we're going to repeat that 40 times. So one trial involves looking at 5 free throws. So we look at the random digit table, and we go to line 106, and we look at the first 5 digits. And she makes 2 free throws, right? 0, 1, 2, 3, 4, or 5 are successes. So here she makes 2 free throws. And then the whole part of this table, 40 simulations, right? So here she makes 5. Here she makes 4. Here she makes 2. Here she makes 2. Here she makes 2. Here she makes all 5. 2. 2. 2. 3. 4. 1. Here she makes all 5. 3. 3. 3. 4. 1. 4. 2, 2, 1, 2, 3, 3. He or she makes all 5. 2, 4, 2, 3, 2, 3, 1, 3, 2, 3, 4, 0, and 2. So we have 1, 2, 3, 4 places where she makes all 5. So we can estimate the probability that she makes 5 out of 5 free throws as being 4 out of 40, which is 10%. True probability is 0.6 to the 5th, which is 7.78%, which isn't that far off. Like, that's not a bad approximation. Okay. For the following, just say how many random digits would be needed to carry out the simulation. So, the probability of getting a prize in a cereal box is 1 out of 10. Use 30 trials of a simulation to estimate the probability of getting one prize, at least one prize, if you buy 5 boxes of cereal. So, assign the digits. Say 0 is a prize. 1 through 9 is no prize. We're buying 5 boxes, so we need 5 digits. To do 30 trials, 30 times 5 is going to be 150. Probability of being a senior at UHS is 0.24. Use 45 trials to estimate the probability that a group of 40 students, there are at least 10 seniors. So here we need 2 digits for each person, right? So 0, 0 to 2, 3 is going to be a senior, and 2, 4 to 9, 9 is going to be not a senior. So we need 2 digits in a group of 40 students. That's going to be it's going to be 80 total. Come on, give me my thingy. That's going to be 80 total. All right, 2 times 40. So 2 digits per student times 40 students, and then we're going to do 45 trials. And that is going to be a total of 3,600. Probability of being a freshman at UHS is 0.26. You will randomly sample groups of 10 freshmen until you get a group that has at least 3 freshmen. So here we don't have a stopping point. So we don't know how many digits we're going to need, because we don't know how many times we're going to have to do this until we get a group with at least 3 freshmen. The probability in an event is 0.534. We want to know the probability that in 2 trials it will happen exactly once. Repeat the simulation 20 times. So we need 3 digits for a 0.534 probability. So from 0, 0, 0 to 533 is the success. From 534 to 999 is the failure. So we need 3 digits. We're doing 2 trials. And we want to repeat this 20 times. So that's going to be 120 digits. And that's it. That's all that there is to simulations. But the AP test wants you to know how to use a random number table because they're stuck in the 1980s.